Greetings. I'm Joe French, and I'm coming to you from my classroom in Mount Pleasant, Utah. And this is topic 2.8, the product rule in the AP Calculus curriculum. Now, the AP Classroom videos have a great proof of the product rule, but let's just go over the reason why we need the product rule. It would be great if when we take the derivative of a product of functions like x squared times x3, we could just take the derivative of each individual term. So the derivative of x squared by the power rule would be 2x, and then we would multiply by the derivative of the second function, x cubed, which would be 3x squared by the power rule. And then if we combine that, we would end up with 6x cubed. But if we applied our properties of exponents, we know that x squared times x cubed is actually x to the fifth, or can be expressed that way. And the derivative of x to the fifth by the power rule is 5x to the fourth. Clearly, these two answers are different. So this just doesn't work. If we applied the same principles to x squared plus 1 times x cubed plus 2, again, our derivatives would be 2x and 3x squared, which would give us that 6x cubed again. But if we multiplied the expressions out by foiling, x squared times x cubed is x to the fifth. That's our first. Our outer would be 2 times x squared. And then our inner term would be 1 times x cubed, and our last terms would just be 2. And if we take the derivative here by the power rule and our sum rule, we would get 5x to the fourth plus 4x plus 3x squared plus 0, because the derivative of a constant is 0. Clearly, these two are not the same. So that's why we have our power rule, where the derivative of a product of two functions equals the first function times the derivative of the second plus the second function times the derivative of the first function. Let's work through a couple of example problems. So here, f of x is 3x squared times the quantity 5x plus 1. And if we remember that our derivative of our product is going to be f first times the derivative of the second plus the second times the derivative of the first. Sometimes you'll see it in reverse order, which is perfectly fine. If you add 3 and 4, you get the same answer as adding 4 and 3. So let's take our formula. We will identify our first function to be 3x squared, and our second function we will identify as 5x plus 1. So our derivative will be our first function, 3x squared, times the derivative of our second function. The derivative of 5x plus 1 is just 5. It's the slope of the line y equals 5x plus 1. And then we add our second function, 5x plus 1, and we multiply by the derivative of our first function. The derivative of 3x squared using the power rule is 6x. At this point, we could end, if we're just answering a free response question, this is a perfectly acceptable expression for the derivative. But more than likely, we would get a question like this on multiple choice, and we would have to simplify. So if we simplify, we take the 3x squared times 5 and get 15x squared, plus distribute the 6x, and we get 30x squared plus 6x, which gives me 45x squared, 15 plus 30, plus 6x. And As you can see, we left it in unsimplified form, which, as again, I am perfectly happy to see. Let's look at another example. Y equals x to the minus 1 plus 2 times the quantity x to the 3 halves plus 1. Now we could try and FOIL this out so that we'd have a single expression where we could take the derivatives of the individual terms, but that looks pretty messy. So let's instead use our formula. My first function is x to the minus 1 plus 2, and then I take the derivative of the second function. And again, we use the power rule, so we bring down the 3 halves, x, and then 3 halves minus 1 is 1 half, and the derivative of the plus 1 is just 0 because the derivative of a constant is 0. And then we add, then we take our second function, which was x to the 3 halves plus 1, and multiply times the derivative of the first function, taking down the negative 1 from the exponent, using it as the coefficient, and then subtracting 1 from negative 1 gives me negative 2, and the derivative of 2, as always, is 0. And there we have our derivative. This would be dy dx. Eureka. Let's look at one more example. Here we have a graph, our infamous graph. Here we have the linear functions f in red and g in blue. And h of x is the function f of x times g of x. We want to find the derivative of h when x equals 3. All right, well, the derivative of h of x, h prime, is our product rule. So f of x times g prime of x plus g of x times f prime of x, the derivative of our first function. So at 3, when x equals 3, f of x is 4. So f of 3 is 4. G of 3, on the other hand, is right here, and that's 1 1/2, or 3 halves. F prime of 3, well, the derivative tells us about the rate of change, right? And the rate of change of a line is constant. So if we look at what's happening to f, we can see that we go over 1 and up 2. So our slope is 2 over 1 everywhere on the curve. So even at x equals 3. So f prime of 3 is going to be 2. G prime of 3 will be the slope of g of x. And there we can see that we go down 1 as we go over 2. So g prime of 3 is negative 1/2. So if we put those numbers into our formula, f of 3 was 4, so h prime of 3 is f of 3 g prime of 3 plus g of 3 f prime of 3. So f of 3 was 4, g prime of 3 was negative 1/2, plus g of 3, which was 3 halves, times f prime of 3, which was 2. Well, 4 times negative 1/2 is negative 2, and 3 halves times 2 is 3. So negative 2 plus 3 is 1. And we have our answer. H prime of 3 equals 1. All right, hopefully these examples will help you apply the product rule in various situations.